So now we're starting to get somewhere with the proof, and I want to do an interlude of doing a few more careful definitions. But first, I want to wave my hands, be general a little bit. What we're really going to see here is there's calculus, and if you're taking an advanced calculus course, proving things in calculus rigorously, you know that it's all based at heart, at least partly on topology, on notions of continuity and limits and epsilons and deltas and all that kind of stuff. Okay, but what I'm going to be emphasizing here is the geometry that's kind of in the middle. Geometry is kind of a finer level of analysis than topology, and the calculus is maybe a still finer level. It's a little bit vague, but not totally accurate. But it's really the interaction of these three ideas that's gonna come in here. So this is notions like continuity and homeomorphism, which we've already talked about a little bit. This is notions like differentiability. Such a long word, takes so long to write. I would just write diff, I guess. Differentiability. And then this is really about distance, and we're going to see this is where the Lipschitz concept that we discovered is going to be necessary to use here. So, for example, Lipschitz, as I said at the end of the last video, it's a more precise and quantitative version of continuity. Continuity just says if you vary the input a little, the output shouldn't vary too much, and it's nicely vague about how much that can be. Lipschitz says, no, there has to be a bounded ratio. There has to be a fixed bound on the secant slope. And that's intermediate between continuity and differentiability. And it's a very useful intermediary. Okay, so the definition, excuse me for clearing my throat so much, sometimes that happens. So the definition is that f, again, it's going to be some function defined on a subset of Rn. Going to Rm is totally fine here because we're backing off a little bit from the specific case of inverse functions, because this is such a useful concept anyway, is Lipschitz. And when I teach this to high school students, they do enjoy saying that word, obviously. And if we want to be specific with Lipschitz constant C, if the variation in the output, actually let me say x1 and x2 because I've been trying to reserve y for the output of f, is less than or equal to c times the variation of the input, just the difference in the inputs, for all x1, x2 in u. Okay, or in other words, if you bring this over here, the secant slope, essentially the ratio of the distance in the outputs, the distance in the inputs, is always bounded by this fixed number c. This is a very, very nice notion. Comes up a lot. It's a nice strengthening of continuity when you really need to have more control over things without insisting something is, say, continuously differentiable, which would be something over here. Now, however, I hope you can tell it's obviously too strong. Think about it for a second. Pause the video. What is just too strong about this definition in our case? Well, it's that it's not local. Okay, so just to save writing, it's locally Lipschitz. Okay, and then there's not going to be one universal constant here. If, let's see if I have enough room, for all x in U, there exists, I'll use the abbreviation, a neighborhood V of x with, this is true, let's say the C can depend on the neighborhood, and this is in V. Okay, so we have one big domain on which this function is defined, and we just need to know that near each point, then wiggling this by some amount gives a controlled amount of wiggling over here, only as much, at most CV times that wiggle if we stay in the neighborhood V. Okay, so locally Lipschitz is a really important concept for us. Whether or not it's said in any proof in any book of this, if you actually know what you're talking about, you see this condition come in any proof I know of the inverse function theorem. So exercise. Okay. Let's see. So one, give examples. So I'm not going to do these for you. I hope they're tractable. I'll probably record a separate video with the solutions to this, but it might take a while. Give examples of, let's say, continuous, a function that's continuous but not Lipschitz. Hint, I gave you that in the last video. Or not even locally. Not even locally Lipschitz. Or, let's say, locally Lipschitz, but not globally Lipschitz, just ordinary Lipschitz. Okay. The hint is secant slopes, and should they be always bounded, or should they just be bounded in any neighborhood? Okay. How about trickier is Lipschitz, but not differentiable. Actually, that's not very tricky. If I just say, what's the most famous example of a non-differentiable function of the first one you ever see, that's a big hint. What else? Okay, so those are good to look at. Oh, and then if you care, it's not going to really come up in here, but you can think about the relationship to a pretty similar, another strengthening of continuity. This is a somewhat less, it's a less geometric strengthening of continuity. There's a relationship to uniform continuity as well, but that doesn't really come up directly. Okay, so now let's think about what we've got. Let's go back to the context that we were looking at this in. We had this function f that goes this way. Okay, from u to, let's say, f of u inside Rn. Okay, so now we're back in the situation of where we got stuck in the proof of the inverse function theorem. And it wasn't f that we needed to know was Lipschitz. It was actually g. It was the inverse function that we assumed that we could find some sort of inverse function, and then we started realizing, of course, we needed to know something about that inverse function, needed to have some nice properties. So it's actually the inverse function g that we wanted to have to be Lipschitz. So what does that mean? Let's look at the one-dimensional case. Oh, and if you want to do this exercise really well, don't just do it. You can find all these guys functions from R to R, but think about it in multiple dimensions as well, at least R2 to R2. Okay. But I'll violate that rule right now, and let's just look at this function. Suppose this is y equals f of x. Okay. What's going to go wrong with trying to invert this function and try to create g, its inverse? It's not where it's steepest. No, it's where it's flattest. In fact, these are points that are just going to give us all kinds of trouble. The derivative is going to go to infinity, and if you try to do it in any neighborhood of that point, it's obviously not even 1 to 1. Okay, so we don't want f, aren't worried too much about it being too steep. We want it to be not too shallow. Okay, so that's going to say that g is not too steep. Because after all, when you invert a function, you flip it across the y equals x line, anything that's particularly low slope becomes a particularly high slope thing. And that's what we were having to worry about. We wanted the secant slopes of the inverse function g to be bounded. We wanted it to be Lipschitz. Okay, so we need, but of course, we need to know what that means about f, because f is our input to this whole problem. So what is it? What is a condition, or a contrition, I guess, a condition on f that would lead to g being Lipschitz? Okay, well, here it is. The secant slopes of f shouldn't be too small, as well as they shouldn't be too big. Okay, so here's the definition. And trust me, I won't just be doing definition after definition. But really, whenever I make a definition, it's something that you're going to see in just about any proof of the inverse function theorem. I'm just giving it a name so we can think about it as a separate issue. F, our usual thing, is I'm going to leave a space. You can probably tell what I'm going to fill it in there. Is by Lipschitz if there are C prime and C with the variation in the output, as usual, it's at most some constant times variation in the input, because that is still a good thing to require. But it's at least C prime, can you see that? Move it over, times the variation in the input. Or in other words, the ratio is always between C prime and C, and these should be positive numbers or else it doesn't mean much. Okay, and obviously C prime should be less than C. Usually, you can jigger this so that the C prime is 1 over C, but I don't think there's, I think it's kind of nice to have them be both floating. It's a little bit easier to deal with. Okay, so again, the idea is that in one dimension, the secant slopes should not be too small. They should never get even close to this kind of thing where they'd be 0. And they shouldn't be too big either, because otherwise you're getting into situations where the functions will behave in the other direction. Okay, but it's actually this that's really more interesting to us. Okay, now let's see if I left enough room. We really want it local. We don't really care if x1 and x2 are across, thousands of miles from each other. That's not the issue here. What we really care about is as they get close to each other, as x1 and x2 get close to each other, f of x1 and f of x2 don't get super, super close, unexpectedly close to each other, so that the slopes collapse. Okay, and I'm going to have to insert it here. For every x, there exists a neighborhood V with this guy. Oh, and of course I didn't even finish the original statement. For every x1, x2, the global statement would be everywhere in U. But now we're going to say on each of these guys. And these are, of course, things that can depend on V. You often don't decorate them, because you often just work with one V at a time, and it's not like you're comparing the different V's necessarily very often. Okay, so it's a mouthful, locally by Lipschitz. But it turns out that that's really the key intermediary between, oops, no, that was my notes for myself. Don't want to give things away. That was his key intermediary, okay? So it's really this locally by Lipschitz condition that shows up is something we're going to show. So we're really looking at, if we can prove that about f, that's going to deal with a lot of these details. It's not going to be the only thing. It's not going to be the thing that really completely nails the proof, but it's actually going to get us towards the right kind of thinking to get the proof. And in particular, okay, some more exercises. Okay, well, again, let me just say, compare to Lipschitz and locally Lipschitz. In other words, find examples that satisfy the weaker conditions but don't satisfy these guys. Pretty easy. I think I just drew one on the previous page. Okay, more interestingly, there's some non-trivial facts pretty easy facts we could do. Locally by Lipschitz, or let's see, by Lipschitz implies 1-to-1. Not super hard, but important to realize. This is just pure set theory. This is a much more stronger condition, but it's nice to know the set theory condition comes out. And in fact, and then locally by Lipschitz is a stronger version of one of the things that we needed to get the whole calculation started, f being locally 1-to-1. So this suggests that we really should show that the f is locally by Lipschitz, and the really key thing is that the inverse is locally by Lipschitz. You can't even see that at all. I shouldn't squeeze it in there. I think I'll close up the video with this one, but let me just write that out, because that's really an important piece of this. Okay, that's why we really care in this case about the locally by Lipschitz condition. So we'll say proposition, but I'm going to have you guys prove it as an exercise until I come back and do the exercises in separate videos. If f is locally by Lipschitz, it is locally 1-to-1, and its local inverses are also locally by Lipschitz. And that's what we wanted. We really want the Lipschitz part for G. We need the by part for F so we can get the Lipschitz part for G. And that was the crucial missing piece in that calculation that would let us conclude that G is actually differentiable. Okay, so this is not super hard to prove. In the next one, I'm going to talk about what other big theorem in calculus connects to this. There's a really big theorem in the foundations of calculus that directly implies that things are Lipschitz, and then we're going to have to be a little more clever about how to get something that's by Lipschitz or locally by Lipschitz. So before you click on the next video, then you should think about, what does he mean? What is this big theorem in the foundations of calculus? And you'll probably be able to guess what it is.